Okay, we've already talked about the power series expansion of a function centered at x equals 0, and that's called the Maclaurin series. In this video, we're generalizing to power series centered about any arbitrary location, and those are called Taylor series. So our goal in this video is to derive a general solution for how to express a Taylor series. Then we're going to apply it to the sine function. And then we're going to use truncated Taylor series, in other words, cutting the series off short, in order to create polynomial approximations to the sine function that are valid near a particular value of x. That's a lot to handle in one video, so let's get started. This is the Taylor series proposal. So the idea is, I think I could represent any well-behaved function as a polynomial. Instead of writing it as powers of x, though, I'm writing it as powers of x minus a. I hope you still agree this is a polynomial. When I expand all of these different powers of this binomial, I could still collect all the powers of x and write it in ascending order if I wanted to. The thing about this representation is that I'm guaranteed that this thing is going to converge very strongly when x is close to a, because powers of x minus a would be powers of a very small thing, and I'll get a series that converges rapidly. So if we can find the c's out of this, then that shows that it's possible to represent this function as a polynomial even if it's infinitely many terms long. And the trick for this is very similar to the trick from Maclaurin series. The first thing I notice is if I evaluate f at x equals a, I get c naught plus c1 times, oh look at that, 0, plus c2 times 0 squared plus, and so on and so on. So every term containing an x minus a factor is going to vanish, and I've already found my first coefficient. Now we have to come up with a strategy for exposing c1, and it's actually just the first derivative that will get that done. So we're assuming here that I have a well-behaved function that I can just keep taking derivatives of. The derivative of x minus a is just 1, so I end up with just a c1. The derivative of x minus a squared, you might think you have to use the chain rule. You would bring down the 2 in front, and then have your x minus a. And the chain rule would say multiply by the derivative of x minus a, but again, that's just 1, so no big deal. My third term. And just to make us very confident that we're detecting the pattern correctly, I'm going to go ahead and extend this to the term that originally started with a power of 4 on it. All right, same trick, plug in x equals a. Every term with an x minus a in it is going to vanish, and you end up with just c1. So we just found that c1, forgot my prime there for a second, c1 is f prime of a. And we continue. I think I can get access to c2 by taking another derivative. That gives me 2c2 plus 3 times 2c3 x minus a plus 4 times 3c4 x minus a squared. And when I evaluate f double prime at x equals a, all the x minus a containing terms are going to vanish, leaving me with 2c2. And I get that c2 is equal to 1/2 f double prime of a. Continuing on to the third derivative, I get 3 times 2 times c3 plus 4 times 3 times 2c4 times x minus a plus other terms that have x minus a's in them. Evaluating that at x equals a, every term vanishes except for the constant out in front. That gives me 3 times 2 times c3, and I end up with c3 equals 1 over 3 times 2 f triple prime of a. And I'll wrap it up with the fourth derivative here because I'm starting to see the pattern. That gives me a 4 times 3 times 2 times c4 out in front, plus additional terms that have powers of x minus a. Those are all going to vanish when I plug in x equals a. And I find that my fourth coefficient is 1 over 4 times 3 times 2, fourth derivative of f evaluated at a. So what we're looking at in these denominators looks like factorials, and I can extend that pattern all the way back to the first term. So I have 1 over 4 factorial, fourth derivative of f evaluated at a. That's how you find c4. c3, 1 over 3 factorial, third derivative evaluated at a. C2, well, 2 is the same as 2 factorial, so I can extend the pattern back. 1 is the same as 1 factorial, so it works for C1 as well. Take the first derivative and evaluate at a. And then 0, 1 over 0 factorial. Well, 0 factorial is 1, so this works too. And I'm sort of saying that computing f of a is like having a 0th derivative. So I generalize and I write down that Cn is 1 over n factorial, nth derivative of my function evaluated at x equals a. Where again, when I plug in 0 into that, the 0th derivative means you don't differentiate at all. You just plug into the original function. And in summation notation, my Taylor series is going to be nth derivative of the function evaluated at a over n factorial multiplying x minus a to the n power. Okay, so now we have a way of expanding any well-behaved function in powers of x minus a, and that's going to converge very quickly when x is close to a. So let's look at an application for Taylor series. In this question, I want to find the Taylor series for the sine function centered at x equals pi over 2. So this power series expansion is going to converge very quickly when x is close to pi over 2. And then what I want to do is start truncating the Taylor series in different spots. These are called Taylor polynomials or Taylor polynomial approximations. And if you plot those Taylor polynomials together with the sine function, you will see that they're extremely close to the sine function as long as x is close to pi over 2. So that's what we're trying to verify here. As a quick reminder, our Taylor series proposal looks like this. And the way it turned out was that our coefficients could be found with this little formula. So in this case, that means we're proposing sine of x is equal to some constant plus another coefficient times x minus pi over 2. Another coefficient x minus pi over 2 quantity squared, and so on and so on. And this is going to converge rapidly when x is very close to pi over 2. So our coefficients are going to involve derivatives of the function that we're working with. So I should probably get some derivatives of the sine function written down. We have sine x, cosine x for the first derivative, negative sine x for the second derivative. Third derivative would be negative cosine x. Fourth derivative, back to sine x. Fifth derivative, cosine x again. So I'm going to look for my constant c0, that's 1 over 0 factorial, which is just 1, times the original function, not differentiated at all, but evaluated at a. So I have sine pi over 2, and that's equal to 1. Then I look for c1. I take 1 over 1 factorial, which is just 1. First derivative of my function evaluated at pi over 2, that's cosine pi over 2. That's 0. Then I look at c2. There's my second derivative. And I'm going to take 1 over 2 factorial. Second derivative evaluated at pi over 2. And that gives me a 1 for that. So I end up with 1 over 2 factorial for my coefficient. C3, I'm working with the third derivative now. It's going to be a 1 over 3 factorial cosine pi over 2 with a minus sign. 0. Then I look at C4. And that's going to be a 1 over 4 factorial, fourth derivative of f evaluated at pi over 2, so sine pi over 2. And that gives me 1 over 4 factorial. And then C5, also going to come out to 0. But just for completeness, I'll write it like I did the others. Cosine of pi over 2 is 0. Okay, so we're able to conclude then that the sine function, sine x, can be written, and I'm looking back here as I write this stuff down, as c0, that was 1, plus c1 times the quantity x minus 2. Well, c1 was 0, so I'm skipping that term. And I just realized I missed a minus sign on c2. I'll just put it in now. So plus c2, which is a negative 1 over 2 factorial, times x minus pi over 2 squared plus, it looks like C4 is the next survivor, and that was a 1 over 4 factorial x minus pi over 2 to the 4th minus, and so on and so on. So there's the series expansion of sine x about x equals pi over 2. Again, when x is very close to pi over 2, these terms get small really fast, higher and higher powers of a small thing. And so the idea with a Taylor polynomial is that you can just truncate this series, and that creates a finite polynomial that's a good approximation of the function that you're looking at as long as you stay close to the expansion point. So our first Taylor polynomial is this one. Sine of x is approximately equal to 1. Our second Taylor polynomial, a little better approximation, is found by keeping the first two terms. Sine of x is approximately 1 minus 1/2 times x minus pi over 2 squared. In other words, we're planning to approximate the sine function with a parabola at that particular point, and it should match up pretty well to the curve of the sine function as long as we stay close to x equals pi over 2. Our third Taylor approximation, sine x approximately equal to 1 minus 1/2 times x minus pi over 2 quantity squared plus 1 over 4 factorial. I'll just expand that real quick. That's 1 over 24. It'll be easier to put into the plotting software that way. So that's our quartic approximation. So let's bring in a graph with the original function and the first three Taylor polynomials on it, and then we'll be done. All right, so here's our image of the original function, sine x, in yellow. And then that first approximation, the constant approximation, is in red. And I can see it matches up with the sine function very well as long as I'm really close to x equals pi over 2 right here. But it doesn't capture any of the curvature of the sine function, so it's not typically a very useful approximation. Then I move on to the quadratic approximation. It's this green upside-down parabola, and it matches up seemingly perfectly to the curvature of the sine function as long as I'm fairly close to x equals pi over 2. If I want to extend my approximation even a little further out, I keep this fourth power term. That's shown in this sort of magenta color, and I can see that matches up incredibly well to the sine function all the way from about here to about here. It's nearly indistinguishable from the curve of the sine function. So as you continue this to higher and higher and higher powers of x, you can create these wiggly polynomials that match up to the sine function, and you can actually take this as far as you want in either direction just by keeping enough terms.